Part 1, Chapter 5 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Aubrey in August 2017. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Chapter 5. Comets. Part 1. Newton showed that the bodies known as comets or hirsute stars obey the law of gravitation, but it was by no means certain that the individual of the species observed by him in 1680 formed a permanent member of the solar system. The velocity, in fact, of its rush round the sun was quite possibly sufficient to carry it off forever into the depths of space, there to wander, a celestial casual, from star to star. With another comet, however, which appeared 2 years later, the case was different. Edmund Halley, who afterwards succeeded Flamsteed as Astronomer Royal, calculated the elements of its orbit on Newton's principles, and found them to resemble so closely those similarly arrived at for comets observed by Peter Apian in 1531 and by Kepler in 1607, as almost to compel the inference that all three were apparitions of a single body. This implied its revolution in a period of about 76 years, and Halley accordingly fixed its return for 1758-9. So fully alive was he to the importance of the announcement that he appealed to a candid posterity, in the event of its verification, to acknowledge that the discovery was due to an Englishman. The prediction was one of the test questions put by science to nature, on the replies to which largely depend both the development of knowledge and the conviction of its reality. In the present instance, the answer afforded may be said to have laid the foundation of this branch of astronomy. Halley's comet punctually reappeared on Christmas Day, 1758, and effected its perihelion passage on the 12th of March following, thus proving beyond dispute that some, at least, of these erratic bodies are domesticated within our system and strictly conform, if not to its unwritten customs, so to speak, at any rate to its fundamental laws. Their movements, in short, were demonstrated by the most unanswerable of all arguments, that of verified calculation, to be calculable, and their investigation was erected into a legitimate department of astronomical science. This notable advance was the chief result obtained in the field of inquiry just now under consideration during the 18th century. But before it closed, its cultivation had received a powerful stimulus through the invention of an improved method. The name of Olbers has already been brought prominently before our readers in connection with asteroidal discoveries. These, however, were but chance excursions from the path of cometary research which he steadily pursued through life. An early predilection for the heavens was fixed in this particular direction by one of the happy inspirations of genius. As he was watching, one night in the year 1779, by the sickbed of a fellow student in medicine at Göttingen, an important simplification in the mode of computing the paths of comets occurred to him. Although not made public until 1797, Olbers's method was then universally adopted, and is still regarded as the most expeditious and convenient in cases where absolute rigor is not required. By its introduction, not only many a toilsome and thankless hour was spared, but workers were multiplied and encouraged in the prosecution of labors more useful than attractive. The career of Heinrich Olbers is a brilliant example of what may be done by an amateur in astronomy. He at no time did regular work in an observatory, he was never the possessor of a transit or any other fixed instrument. Moreover, all the best years of his life were absorbed in the assiduous exercise of a toilsome profession. Born in 1758 at the village of Arbergen, where his father was pastor, he settled in 1781 as a physician in the neighboring town of Bremen, and continued an active practice there for over 40 years. It was thus only the hours which his robust constitution enabled him to spare from sleep that were available for his intellectual pleasures. Yet his recreation was, as von Zach remarked, no less prolific of useful result than the severest work of other men. The upper part of his house in the Sandgasse was fitted up with such instruments and appliances as restrictions of space permitted, and there, night after night during half a century and upwards, he discovered, calculated, or observed the cometary visitants of northern skies. Almost as effective in promoting the interests of science as the valuable work actually done by him was the influence of his genial personality. He engaged confidence by his ready and discerning sympathy, he inspired affection by his benevolent disinterestedness, he quickened thought and awakened zeal by the suggestions of a lively and inventive spirit, animated with the warmest enthusiasm for the advancement of knowledge. Nearly every astronomer in Germany enjoyed the benefits of a frequently active correspondence with him, and his communications to the scientific periodicals of the time were numerous and striking. The motive power of his mind was thus widely felt and continually in action. Nor did it wholly cease to be exerted even when the advance of age and the progress of infirmity rendered him incapable of active occupation. He was, in fact, alive even to the last day of his long life of 81 years, and his death, which occurred March 2, 1840, left vacant a position which a rare combination of moral and intellectual qualities had conspired to render unique. Amongst the many younger men who were attracted and stimulated by intercourse with him was Johann Franz Encke. But while Olbers became a mathematician because he was an astronomer, Encke became an astronomer because he was a mathematician. A born geometer, he was naturally sent to Göttingen and placed under the tuition of Gauss. But geometers are men, and the contagion of patriotic fervor which swept over Germany after the Battle of Leipzig did not spare Gauss's promising pupil. He took up arms in the Hanseatic Legion, and marched and fought until the oppressor of his country was safely ensconced behind the ocean walls of St. Helena. In the course of his campaigning he met Lindenau, the militant director of the Seeberg Observatory, and by his influence was appointed his assistant, and eventually, in 1822, became his successor. Thence he was promoted in 1825 to Berlin, where he superintended the building of the new observatory, so actively promoted by Humboldt, and remained at its head until within some 18 months of his death in August 1865. On the 26th of November 1818, Pons of Marseille discovered a comet whose inconspicuous appearance gave little promise of its becoming one of the most interesting objects in our system. Encke at once took the calculation of its elements in hand, and brought out the unexpected result that it revolved round the sun in a period of about 3⅓ years. He, moreover, detected its identity with comets seen by Méchain in 1786, by Caroline Herschel in 1795, by Pons, Hutt, and Bouvard in 1805, and after 6 laborious weeks of research into the disturbances experienced by it from the planets during the entire interval since its first ascertained appearance, he fixed May 24, 1822, as the date of its next return to perihelion. Although on that occasion, owing to the position of the earth, invisible in the northern hemisphere, Sir Thomas Brisbane's observatory at Parramatta was fortunately ready equipped for its recapture, which Rümker effected quite close to the spot indicated by Encke's ephemeris. The importance of this event can be better understood when it is remembered that it was only the second instance of the recognized return of a comet, that of Halley's, 63 years previously, having, as already stated, been the first, and that it, moreover, established the existence of a new class of celestial object, somewhat loosely distinguished as comets of short period. These bodies, of which about 30 have been found to circulate within the orbit of Saturn, are remarkable as showing certain planetary affinities in the manners of their motions not at all perceptible in the wider travelling members of their order. They revolve, without exception, in the same direction as the planets, from west to east. They exhibit a marked tendency to conform to the zodiacal track which limits planetary excursions north and south, and their paths around the Sun, although much more eccentric than the approximately circular planetary orbits, are far less so than the extravagantly long ellipses in which comets comparatively untrained, as it were, in the habits of the solar system ordinarily perform their revolutions. No great comet is of the planetary kind. These are, indeed, only by exception visible to the naked eye. They possess extremely feeble tail-producing powers, and give small signs of central condensation. Thin wisps of cosmical cloud, they flit across the telescopic field of view without sensibly obscuring the smallest star. Their appearance, in short, suggests, what some notable facts in their history will presently be shown to confirm, that they are bodies already effete and verging towards dissolution. If it be asked what possible connection can be shown to exist between the shortness of period by which they are essentially characterized and what we may call their superannuated condition, we are not altogether at a loss for an answer. Kepler's remark that comets are consumed by their own emissions has undoubtedly a measure of truth in it. The substance ejected into the tail must, in overwhelmingly large proportion, be forever lost to the central mass from which it issues. True, it is of a nature inconceivably tenuous, but unrepaired waste, however small in amount, cannot be persisted in with impunity. The incitement to such self-spoliation proceeds from the Sun. It accordingly progresses more rapidly the more numerous are the returns to the solar vicinity. Comets of short period may thus reasonably be expected to wear out quickly. They are, moreover, subject to many adventures and vicissitudes. Their aphelia, or the farthest points of their orbits from the Sun, are usually, if not invariably, situated so near to the path either of Jupiter or of Saturn as to permit these giant planets to act as secondary rulers of their destinies. By their influence they were, in all likelihood, originally fixed in their present tracks, and by their influence, exerted in an opposite sense, they may, in some cases, be eventually ejected from them. Careers so varied, as can easily be imagined, are apt to prove instructive, and astronomers have not been backward in extracting from them the lessons they are fitted to convey. Encke's comet, above all, has served as an index to much curious information, and it may be hoped that its function in that respect is by no means at an end. The great extent of the solar system traversed by its eccentric path makes it peculiarly useful for the determination of the planetary masses. At perihelion it penetrates within the orbit of Mercury. It considerably transcends at aphelion the farthest excursion of Pallas. Its vicinity to the former planet in August 1835 offered the first convenient opportunity of placing the body in the astronomical balance. Its weight or mass had previously been assumed, not ascertained, and the comparatively slight deviation from its regular course impressed upon the comet by its attractive power showed that it had been assumed nearly twice too great. That fundamental datum of planetary astronomy, the mass of Jupiter, was corrected by similar means, and it was reassuring to find the correction in satisfactory accord with that already introduced from observations of the asteroidal movements. The fact that comets contract in approaching the Sun had been noticed by Hevelius. Pingré admitted it with hesitating perplexity. The example of Encke's comet rendered it conspicuous and undeniable. On the 28th of October 1828, The diameter of the nebulous matter composing this body was estimated at 312,000 miles. It was then about 1½ times further from the Sun than the Earth is at the time of the equinox. On the 24th of December following, its distance being reduced by nearly 2/3, it was found to be only 14,000 miles across. That is to say, it had shrunk during those 2 months of approach to 1/11,000th part of its original volume. Yet it had still 17 days' journey to make before reaching perihelion. The same curious circumstance was even more markedly apparent at its return in 1838. Its bulk, or the actual space occupied by it, appeared to be reduced, as it drew near the hearth of our system, in the enormous proportion of 800,000 to 1. A corresponding expansion accompanied on each occasion its retirement from the sphere of observation. Similar changes of volume, though rarely to the same astounding extent, have been perceived in other comets. They still remain unexplained, but it can scarcely be doubted that they are due to the action of the same energetic internal forces which reveal themselves in so many splendid and surprising cometary phenomena. Another question of singular interest was raised by Encke's acute inquiries into the movements and disturbances of the first known comet of short period. He found from the first that its revolutions were subject to some influence besides that of gravity. After every possible allowance had been made for the pulls, now backward, now forward, exerted upon it by the several planets, there was still a surplus of acceleration left unaccounted for. Each return to perihelion took place about 2½ hours sooner than received theories warranted. Here, then, was a residual phenomenon of the utmost promise for the disclosure of novel truths. Encke, in accordance with the opinion of Olbers, explained it as due to the presence in space of some such subtle matter as was long ago invoked by Euler to be the agent of eventual destruction for the fair scheme of planetary creation. The apparent anomaly of accounting for an accelerative effect by a retarding cause disappears when it is considered that any check to the motion of bodies revolving round the center of attraction causes them to draw closer to it, thus shortening their periods and quickening their circulation. If space were filled with a resisting medium capable of impeding, even in the most infinitesimal degree, the swift course of the planets, their orbits should necessarily be, not ellipses, but very close elliptical spirals along which they would slowly, but inevitably, descend into the burning lap of the Sun. The circumstance that no such tendency can be traced in their revolutions by no means sets the question at rest. For it might well be that an effect totally imperceptible until after the lapse of countless ages, as regards the solid orbs of our system, might be obvious in the movements of bodies like comets of small mass and great bulk, just as a feather or a gauze veil at once yields its motion to the resistance of the air, while a cannon ball cuts its way through with comparatively slight loss of velocity. It will thus be seen that issues of the most momentous character hang on the time-keeping of comets, for plainly all must in some degree suffer the same kind of hindrance as Encke's, if the cause of that hindrance be the one suggested. None of its congeners, however, show any trace of similar symptoms. True, the late Professor Oppolzer announced in 1880 that a comet, first seen by Pons in 1890 and rediscovered by Winnecke in 1858, having a period of 2052 days, 5.6 years, was accelerated at each revolution precisely in the manner required by Encke's theory. But M. von Hertel's subsequent investigation, the materials for which included numerous observations of the body in question at its return to the Sun in 1886, decisively negatived the presence of any such effect. Moreover, the researches of Van Asten and Backlund into the movements of Encke's comet revealed a perplexing circumstance. They confirmed Encke's results for the period covered by them, but exhibited the acceleration as having suddenly diminished by nearly 1/2 in 1868. The reality and permanence of this change were fully established by observations of the ensuing return in March 1885. Some physical alteration of the retarded body seems indicated, but visual evidence countenances no such assumption. In aspect, the comet is no less thin and diffuse than in 1795 or in 1848. The character of the supposed resistance in interplanetary space has, it may be remarked, been often misapprehended. What Encke stipulated for was not a medium equally diffused throughout the visible universe, such as the ethereal vehicle of the vibrations of light, but a rare fluid, rapidly increasing in density towards the sun. This cannot be a solar atmosphere, since it is mathematically certain, as Laplace has shown, that no envelope partaking of the sun's axial rotation can extend farther from his surface than 9/10 of the mean distance of Mercury, while physical evidence assures us that the actual depth of the solar atmosphere bears a very minute proportion to the possible depth theoretically assigned to it. That matter, however, not atmospheric in its nature, that is, neither forming one body with the sun, nor altogether aeriform, exists in its neighborhood, can admit of no reasonable doubt. The great lens-shaped mass of the zodiacal light, stretching out at times far beyond the earth's orbit, may indeed be regarded as an extension of the corona, the streamers of which themselves mark the wide diffusion, all round the solar globe, of granular or gaseous materials. Yet comets have been known to penetrate the sphere occupied by them without perceptible loss of velocity. The hypothesis, then, of a resisting medium receives at present no countenance from the movements of comets, whether of short or of long periods. Although Encke's comet has made 35 complete rounds of its orbit since its first detection in 1786, it shows no certain signs of decay. Variations in its brightness are, it is true, conspicuous, but they do not proceed continuously. The history of the next known planet-like comet has proved of even more curious interest than that of the first. It was discovered by an Austrian officer named Wilhelm von Biela at Josefstadt in Bohemia, February 28, 1826, and 10 days later by the French astronomer Gambart at Marseille. Both observers computed its orbit, showed its remarkable similarity to that traversed by comets visible in 1772 and 1805, and connected them together as previous appearances of the body just detected by assigning to its revolutions a period of between 6 and 7 years. The two brief letters conveying these strikingly similar inferences were printed side by side in the same number of the Astronomische Nachrichten, number 94, but Biela's priority in the discovery of the comet was justly recognized by the bestowal upon it of his name. The object in question was at no time, subsequently to 1805, visible to the naked eye. Its aspect in Sir Johann Herschel's great reflector on the 23rd of September 1832 was described by him as that of a conspicuous nebula, nearly 3 minutes in diameter. No trace of a tail was discernible. While he was engaged in watching it, a small knot of minute stars was directly traversed by it, and when on the cluster, he tells us, it presented the appearance of a nebula resolvable and partly resolved into stars, the stars of the cluster being visible through the comet. Yet the depth of cometary matter through which such faint stellar rays penetrated undimmed was, near the central parts of the globe, not less than 50,000 miles. It is curious to find that this seemingly harmless, and we may perhaps add effete body, gave occasion to the first, and not the last, cometary scare of an enlightened century. Its orbit at the descending node may be said to have intersected that of the Earth, since, according as it bulged in or out under the disturbing influence of the planets, the passage of the comet was effected inside or outside the terrestrial track. Now, certain calculations published by Olbers in 1828 showed that, on October 29, 1832, a considerable portion of its nebulous surroundings would actually sweep over the spot which, a month later, would be occupied by our planet. It needed no more to set the popular imagination in a ferment. Astronomers, after all, could not, by an alarmed public, be held to be infallible. Their computations, it was averred, which a trifling oversight would suffice to vitiate, exhibited clearly enough the danger, but afforded no guarantee of safety from a collision, with all the terrific consequences frigidly enumerated by Laplace. Nor did the panic subside until Arago formally demonstrated that the Earth and the comet could by no possibility approach within less than 50 millions of miles. The return of the same body in 1845-46 was marked by an extraordinary circumstance. When first seen, November 28, it wore its usual aspect of a faint round patch of cosmical fog, but on December 19, Mr. Hind noticed that it had become distorted somewhat into the form of a pear, and 10 days later it had divided into two separate objects. This singular duplication was first perceived at New Haven in America December 29 by Messrs. Herrick and Bradley, and by Lieutenant Maury at Washington January 13, 1846. The earliest British observer of the phenomenon, noticed by Wichmann the same evening at Königsberg, was Professor Challis. "I see 2 comets," he exclaimed, putting his eye to the great equatorial of the Cambridge Observatory on the night of January 15. Then, distrustful of what his senses had told him, he called in his judgment to correct their improbable report by resolving one of the dubious objects into a hazy star. On the 23rd, however, both were again seen by him in unmistakable cometary shape, and until far on in March (Otto Struve caught a final glimpse of the pair on the 16th of April) continued to be watched with equal curiosity and amazement by astronomers in every part of the northern hemisphere. What Seneca reproved Ephorus for supposing to have taken place in 373 B.C., what Pingré blamed Kepler for conjecturing in 1618, have then actually occurred under the attentive eyes of science in the middle of the 19th century. At a distance from each other of about 2/3 the distance of the moon from the earth, the twin comets meantime moved on tranquilly, so far at least as their course through the heaven was concerned. Their extreme lightness, or the small amount of matter contained in each, could not have received a more signal illustration than by the fact that their revolutions round the sun were performed independently, that is to say, they travelled side by side without experiencing any appreciable mutual disturbance, thus plainly showing that at an interval of only 157,250 miles their attractive power was virtually inoperative. Signs of internal agitation, however, were not wanting. Each fragment threw out a short tail in a direction perpendicular to the line joining their centres, and each developed a bright nucleus, although the original comet had exhibited neither of these signs of cometary vitality. A singular interchange of brilliancy was, besides, observed to take place between the coupled objects, each of which alternately outshone and was outshone by the other, while an arc of light, apparently proceeding from the more lustrous, at times bridged the intervening space. Obviously, the gravitational tie, rendered powerless by exiguity of matter, was here replaced by some other form of mutual action, the nature of which can as yet be dealt with only by conjecture. Once more, in August 1852, the double comet returned to the neighbourhood of the sun, but under circumstances not the most advantageous for observation. Indeed, the companion was not detected until September 16, when Father Secchi at Rome perceived it to have increased its distance from the originating body to 1,25 millions of miles, or about 8 times the average interval at the former appearance. Both vanished shortly afterwards, and have never since been seen, notwithstanding the eager watch kept for objects of such singular interest, and the accurate knowledge of their track supplied by Santini's investigations. A dangerously near approach to Jupiter in 1841 is believed to have occasioned their disruption, and the disaggregating process thus started was likely to continue. We can scarcely doubt that the fate has overtaken them which Newton assigned as the end of all cometary existence. Diffundi tandem et spargi per coelos universos. End of chapter 5, part 1.